Hi everyone, we have learned a lot about proofs. Today, let's learn the last important topic of Chapter 2, 2.4, Mathematical Induction. So, mathematical induction helps us to show that the statements are true for all natural numbers and that's greater or equal to 1. So here, where the domain of disclosure is n greater or equal to 1, so that is the positive integers. Okay, that is the domain of disclosure. And we have two cases. First, this we also call the base case. The base case is show that the statement 1 is true. So we plug in n equals 1 here. Okay? And then we have the inductive case. We show that the statement k minus 1 implies that the statement k is true for all k greater than 1. Okay? So these are the two steps of inductions. So after we show both cases, we can conclude that by induction, S of k is true for all n greater or equals 1. Okay. There are other textbooks use slightly different. For example, our textbook, the base case is the same, but for the inductive case, instead they assume for any k greater or equal to 1, S of k implies S of k plus 1. And this is the book's notation. Okay. However, I like our way better because at the end you see S of k, and S of k match with Sn. You simply just replace n by k, so it's more easy to see the formula in this way. So but you can use either way, but just make sure to be consistent. Okay. All right, let's continue. So let's look at the example. We want to use induction to verify the following equations. Part A, 1 plus 3 plus 5 plus 2n plus 1 minus 1 equals n squared. Okay, so first step, we want to show the base case. What's the base case? Look at your n. This is the formula of your n. What n can give us 1? Well, this corresponds to n equals 1. Then 2 times 1 minus 1 is 1. N is 1 because when you plug n is 1 here, 2 times n minus 1 equals 1. It's not because of this number 1 is n is 1. Okay? It is because this expression matches the 1 if n equals 1. So we know the base case n is 1. Okay, so when we plug in n is 1, the left-hand side is just 1. The right-hand side is 1 squared. And of course, they are equal, so we get yes. That's the base case. Second is the inductive case. Oops. I just realized I have a typo. Okay, inductive case, we say for any k greater than 1, we assume that S of k minus 1 is true, which means we replace n by k minus 1. So we have 1, 3, 5, plus plus 2. And we place n by k minus 1 equals n, replace n by k minus 1. Here, the typical error is didn't forget the parentheses. So this is actually 2k minus 2 minus 1. This is 2k minus 3. Okay, so we assume that for any k greater than 1, the statement is for k minus 1 is true. Okay. Why do we restrict to have k greater than 1 because we are having k minus 1. So if k is 2, then k minus 1 is 1. We get the base case. But we cannot have k equals 1 then because 1 minus 1 is 0. It's not defined. So k has to be strictly greater than 1 in this case. Okay, so this is the hypothesis. And we want to show that 1 plus 3 plus 5 plus ... plus 2 replace n by k, okay? So we want to show the statement k is true. So here we have 2k minus 1. But there is a previous term. What's the previous term here? Well, that's the 2k plus 3. Okay? And what do we want to show? We want to show this guy at the end equals k squared. So this is the good thing about using this method. K minus 1 implies k, because at the end you know that, oh, okay, we simply just replace n by k. You know, this is our goal. So this is like the island we start with, and this is the island that we're going to. This is our final destination, and then we want to build the bridges between them. Okay, and how do we build the bridges between them? We use the hypothesis. Okay, so we want to use this guy hypothesis. Okay, let's compare. Let me highlight. What are the terms using the hypothesis? 1, 3, 5, up to 2k minus 3, right? And that equals, what does that equal to? K minus 1 squared, right? And we also have one more term, that is 2k minus 1. Okay, let's continue. Here we can multiply out. Well, that is k squared minus 2k plus 1, then plus 2k minus 1. Oh, do you see what happened? The 2k cancel, the 1 cancel. We only left with k squared. Awesome! That is what we want. See, we have built the bridges, connect them. Okay. Finally, we can say by induction, we have the equation holds for all n greater equals 1. Okay, I don't want to copy the equation again, so I just mentioned the equation holds for all n greater equals 1. So far, so good, everybody? Alright, let's continue. Okay, so this is part B. Step 1, base case. What is n? Look at the formula. What n can give us this number? Well, n equals 1, right? When n equals 1, we get this 1 times 2. So base case is when n equals 1. And then on the left-hand side, we have 1 times 2. On the right-hand side, we want to see whether that equals n is 1. 1 plus 1, 2. 1 plus 3, 3. Oh, are they equal? Yes. So base case is true. Second, the inductive case. So we want to assume for any k greater than 1, and our equation holds for k minus 1. So we place n by k minus 1. Then this is k minus 1. When we add 1, become k, and then we have k plus 1 or 3. So we assume this holds, and we want to prove what? The equation holds for n equals k, right? N equals k, then we have k plus 1, right? What's the previous term? The previous term is k minus 1 and k. I want to write out this extra term, then you can see I'm using the hypothesis. Oops, here. Our hypothesis, this guy, equals what? Okay, equals k minus 1 times k k plus 1 over 3. We still have one more term, k plus 1. Okay, what is that? Do you see any common factor? Do you see the common factor k times k plus 1? If you see a common factor, factor that out. Don't multiply everything out and combine the terms, because at the end you still need to factor it. And this is a degree 3 polynomial. In general, it's hard to factor degree 3 polynomial. For degree 2 quadratic functions, we have the quadratic formula, but in general, degree 3 polynomial, we have to use sometimes the rational root theorem. Okay, so continue. So what's left? K minus 1 over 3, and this is 1. Oh, let's take the common denominator is 3, then we have k minus 1 plus 3. Oh, so that is k plus 1. This becomes k plus 2. So far, so good, everybody. Let's see. Ooh, does this guy match? Yes, it matched. We just replace k by n, then we get the original equation, right? So yes, so we have shown that the statements holds for n equals k. Then we say by induction, I don't want to copy this equation, so I just say the equation holds for all n greater equals 1, and we're done. So far, so good, everybody. Okay, let's continue. Okay, let's look at this example. Use induction to show that if r is not 1, then this is true for all n greater equals 1. Oh, sorry, greater equal to 0. So you can see here, in fact, I want to put a remark here. N does not necessarily start with 1, and can start with any possible integer. Okay, so or 0. Okay, so we mark and does not need to start with 1. It can start with other numbers, but you just be careful. The base case, your n will change. Okay, so your n will change. In this case, we change to 0. Okay, so let's continue. Okay, so first, base case. So base case, it means that n equals 0 when n is 0. So let's look at this formula. When we plug in n is 0, we get r to the 0 is 1. So we just have a on the left hand side. On the right hand side, we have a, n is 0. So r to the 1 is r minus 1, r minus 1. Because r is not 1, so we can cancel it. Then we have a equals 8. Yes, that is true. Okay, and then next we have the inductive case. So we assume for k greater than 0, the equation holds for n equals k minus 1. Okay, and what do we want to show? We want to show the equation. Okay, so we know it's ar to the n. So let's the equation holds for k. Okay, so let's put the previous term, so then we can use hypothesis. Okay, so now let's use the okay. Let's use my highlighter. So we want to use the hypothesis. So this guy equals a r to the k minus 1 over r minus 1. We still have one more term, a r to the k. Okay, what is this guy? Can you see a common factor? Well, a common factor is a, right? So let's factor out the a, and then what's left? We have r to the k minus 1 over r minus 1 and r to the k, right? Oh, what is this guy? So we can take the common denominator, and this is r to the k minus 1 plus r to the k times r minus 1. What is this? Well, r to the k times r is r to the k plus 1. R to the k times minus 1 is minus r to the k. Oh, you see r to the k cancel? And let's put it as r to the k plus 1 minus 1 and all over r minus 1. Well, this is exactly what we are looking for. See, it matched with our formula when we replace k by n. So now we have shown the inductive case. So we can say by induction, okay, equation holds, or say the statement is true for all n greater or equals 0. Okay? So far, so good, everybody? All right. Let's continue. Example, use induction to verify the following inequalities. So we not only can use induction to prove equations, we can actually use induction to prove all the statements. Okay, the base case, we show that statement 1 involving k n equals 1 is true, and then inductive case assume that statement k minus 1 is true, and we want to show that statement k is true. Okay, so let's look how to solve the how to prove these inequalities. So first, we have the base case. Well, base case, you can see n equals 1. So n equals 1, what's the left-hand side? Well, the left-hand side equals my formula 2n minus 1. 2n minus 1, 2 minus 1 is 1. Left-hand side is 1, and then 2n is 2. So left-hand side is 1/2, right? And then what is the right-hand side? The right-hand side equals, when we plug in n is 1, 1 over root 2. Ooh, this is true? Look at the denominator, 2 and square root 2. Which one is bigger? Of course, 2 is bigger because square root 2 is like 1.414. Then when we flip it in the denominator, the inequality also flip. That's why we know, okay, yes, this is true. So far, so good, everybody? Okay, second inductive case. So we assume for any k greater than 1, the inequality is true. So we have 1 times 3 times 5, dot, dot, dot. Okay, 2, when we plug in n is k minus 1. And 2, 4, 6, dot, dot, dot. 2 times n is k minus 1. Don't forget the parentheses, okay? So actually, this guy is 2k minus 2 minus 1. Which is 2k minus 3. This guy is 2k minus 2. Okay, and this guy is less than equal to square root of, and replace it by k minus 1. K minus 1 plus 1 is k. So we suppose this is true. Okay, this inequality is true. And we want to show 1 times 5 times 1 times 3 times 5 times ... times we place n by k minus 1. The previous term is 2k minus 3. I want to write the previous term because I want to use my hypothesis. Okay, now I'm going to use my hypothesis. So let me use highlighter. This guy is my hypothesis. I use my hypothesis. This guy is less than equal to what? So it's less than equal to 1 over square root of k. And we still have one more term, 2k minus 1 over 2k, right? And what do we want? We want to show this guy is less than equal to 1 over, we place n by k, so k plus 1. This is what we want to show. Well, how do we show this? Well, it's hard to show this way, but let's figure out what is it equivalent to. So we say equivalently. Okay, we can both sides multiply by, we can clear all the denominator. We multiply both sides. Okay, so multiply both sides by square root of k and 2k and square root of k plus 1. And then because all of these numbers are positive, so it won't change the inequality. So we will have square root of k plus 1 times 2k minus 1 less than equal square root of k times 2k. Alright, so we can, because both sides are positive numbers, we can square both sides. And all of these lines are equivalent, okay? So we have k plus 1, 2k minus 1 squared less than equal to k, 2k squared. Okay, what is this guy? K minus k plus 1, and this is 4k squared minus 4k plus 1. Well, that's k times 4k squared. Okay, now let's continue. Let's multiply everything out. We have k times of these, so 4k cubed minus 4k squared plus k, and then plus 4k squared minus 4k. Yeah, we're multiplying everything out. Plus 1 times 1 is 1. This is the left hand side. The right hand side, we have 4k cubed. Okay, you see 4k cubed cancel. And 4k squared cancel. What do we have? We have k minus 4k. So negative 3k plus 1 less than equal to 0. Oh, what does that mean? We can both sides add the 3k. We get 1 less than equal to 3k. Then k is greater equal to both sides divided by 3, 1/3. Well, this is true because our k is greater than 1. So, of course, it's greater than equal to 1/3. So, because this is true, then all the previous inequalities holds because they are all equivalents. That's why we get this guy is true. Okay, our statement k is true. Then we say by induction. Oh, I ran out of space. Okay, at the end, we say by induction inequality. So inequality is true for k greater equals 1. For n greater equals 1, sorry. Okay, I ran out of space. Sorry about that. Okay, so far so good. Yeah, so sometimes maybe the things you want to show is not so obvious, like what we did before. You you can just multiply everything out and simplify, you get the answer. No, then you have to consider this inequality and consider what is equivalent to this inequality and try to show that. Okay, this is really good examples. All right, let's continue. We want to use induction to prove that 3 to the n plus 7 to the n minus 2 is divisible by 8 for all n greater or equals 1. Okay, so you see this statement, this is just a statement involving n. It's not an equation, it's not an inequality. It's just a statement in general. Okay? So the base case is, what is the n? And start with 1, right? So we plug in 1 there. We have 3 plus 7 minus 2. Oh, that's 8. Of course, 8 is divisible by 8. Okay, so second inductive case. Inductive case, we want to assume for k greater than 1, 3 to the k minus 1. See, we place n by k minus 1, so the statement k minus 1 is true. So this guy is divisible by 8. What does divisible by 8 mean? I would say it means 3 to the k minus 1 plus 7 to the k minus 1 plus 2. Oh, sorry, it's minus 2. Equals 8 times m for some integer m. This is divisible by 8 mean. Okay, and we want to show the statement is true for n equals k. So 3 to the k plus 7 to the k minus 2. We want to show this guy is also divisible by 8. So usually when you want to show this statement, you want to kind of relate it to the hypothesis. So you want to see the terms 3 to the k minus 1 and 7 to the k minus 1. So what we do is we can split one of the 3, and then what's left is 3 to the k minus 1. We can split the 7, and then what's left is 7 to the k minus 1 minus 2. Okay, how do we use our hypothesis? Okay, I'm gonna replace 7 to the k. Let's see here. So look at this guy. We're gonna solve for 7 to the k minus 1. What is this guy? Well, this is 8m, then plus 2, and then minus 3 to the k minus 1. Okay, then I use this guy to plug in here. And then what do we have now? We have 3 times 3 to the k minus 1 plus 7 times, okay, put in here. So 8m plus 2 minus 3k minus 1. And then we still have minus 2. You might ask, oh, why do we solve for 7 to the k minus 1 instead of 3 to the k minus 1? Of course, you can solve the 3 to the k minus 1. Actually, here we have 2 ways to solve this problem. You can also solve for 3 to the k minus 1 and then plug in here. Okay? Yeah, we can do that. There are many ways to solve the problem. So, yeah. Okay. Let's continue. So this is 3 times 3 to the k minus 1. Let's multiply out. 7 times 8, that is 56. 7 times 2, 14. And then we have 7 times 3 to the k minus 1, minus 2. Okay, combine the like terms. So what do we have? Okay, so we have, this is the like terms. 3 minus 7 is negative 4 times 3 to the k minus 1 plus 56m, and 14 minus 2 is 12, right? So we have this guy is plus 12. So far, so good, everybody? Okay. All right, let's continue. Okay, how do we solve here? So this guy is divisible by 8, so that's good. But how about the remaining two terms? So the remaining two terms, the trick is you consider this guy is 12, right? Can we also find a 12 in the first term? Yes, we can do it by splitting the 4 and 3. And then we have 3 to the k minus 2. And because k is greater than 1, k minus 2 is greater equals 0. So is defined. Okay, we can do that. And then we have plus 12. Let's see. So we have 56m. And then now this guy is 12. We can factor out the 12. And then we have 1 minus... let's see. Okay. We have factor out negative 12, then we have 3 to the k minus 2 minus 1. Okay, so now this guy is divisible by 8. That's good. But this guy, 12, is divisible by 4, right? So we are only left to show that this guy is divisible by 2. If we can show this guy is divisible by 2, then the products will be divisible by 8. So now it's left to show 3 to the k minus 2 minus 1 is divisible by 2. Okay, and why is that? Think about 3 to the k minus 2. This is odd numbers or even numbers. This is an odd number. Right, everybody? All the powers of 3 are odd numbers. Okay? Because odd numbers times odd numbers is odd numbers. So, yeah, this is a product of 3. They're odd numbers. Then we have 3 to the k minus 2 minus 1 is even number. Yeah, because it's an even number, so it's divisible by 2. Since it's divisible by 2, then the whole thing here is divisible by 8. Now we have complete the proof. So we say, hence, okay, so we say by induction, we have 3 to the n plus 7 to the n minus 2 is divisible by 8. And that completes the proof. Yeah, this problem is quite challenging, right? So you want to play with it, and then you want to decompose the problem, and then look at each term. Our goal is divisible by 8. Then realize here we have a 12, there have a 12. We can factor out the 12, and our goal is divisible by 8. The 12 has a factor 4. So it means the remaining factor we need it to be divisible by 2. And then we realize it's an even numbers. So this holds. So far, so good. Okay, so this is the last session of chapter 2 we cover in our course. Okay, and that's it for the proof. And then next chapter is gonna be chapter 3. We'll talk about functions, series, and relations. Okay? Have a nice day. Bye.